One of the fundamental concepts in the mechanics section is an understanding of vectors. And we know that vectors are physical quantities that have both magnitude and direction. We know that a physical quantity is anything that we can measure. The most common vectors that we will be dealing with are displacement, which is measured in meters, velocity measured in meters per second, acceleration measured in meters per second, forces that are measured in newtons, and momentum, which is measured in kilogram meters per second. Now, vectors have a number of unique properties. The first one is that vectors can be added together in any order, which, if we look at the example here of somebody who has moved or traveled 5 kilometers east, and then 7 kilometers north, and then 4 kilometers east, there are 3 different ways in which we can show this. All of them start with this person in the same position. The first one shows, in the order that it's done, a movement of 5 kilometers east, followed by a movement of 7 kilometers north, which is then followed by a movement of 4 kilometers east to end up at the final point. Now, to illustrate this point, we can show that somebody who had followed these exact same vectors but in a different direction or in a different order would still end in the same place, whereas if they had first traveled 7 kilometers north, then 5 kilometers east, and then 4 kilometers east again, we would find that they would end in exactly the same place. And finally, the third way in which this could have been done would have been first by going 5 kilometers east, and then 4 kilometers east, and then 7 kilometers north. All of this illustrates that the order in which vectors are added does not matter as long as they maintain their magnitude and direction. The second common property of vectors, or the second common use for vectors, is that since they all start and end in the same place when they are added together, it is possible to determine what is called a resultant vector, meaning the one vector that could replace those other 3 vectors. In this case, that would be the one vector that goes from the starting point directly to the end point. Now, what we can see is that this vector is directed at some angle theta that we can now determine, and we would start by naming each of these planes in which we are moving. So the most common naming conventions here are that this vector over here is acting in the y plane, so we call it the y component. This vector over here is acting in the x plane, so we call it the x component, and then we can call this vector over here our resultant vector. As we can see, we now have a right-angled triangle, and a right-angled triangle allows us to use Pythagoras, which says that the resultant vector squared is equal to the x component squared plus the y component squared. In this case, that gets us an answer of the 2 combined x components are 9 squared plus the y component 7 squared, and therefore our resultant is equal to the square root of 9 squared plus 7 squared, which is 11.40 kilometers. So what we are saying is that if this person had traveled 11.40 kilometers from the starting point in this direction, they would have ended in exactly the same place as the person who followed those 3 vectors. Now, obviously, because this is a vector, the direction is also important. And so what we can see is that we have a right-angled triangle with an angle theta that allows us to use any one of our trigonometric functions. First one I will use is tan of theta. We know that tan of theta is always equal to the opposite side of the triangle over the adjacent side of the triangle. In this case, that is the y component over the x component, and we can substitute our values. The y component we determined was 7, the x we found was 9, and we can then use our second function on the calculator to find that that angle theta is equal to 37.87 degrees. What this now tells us is that these three vectors can be combined to find a resultant vector, which would mean that it would have exactly the same magnitude and direction as those three vectors combined if this person were to travel 11.4 kilometers at an angle of 37.87 degrees. Distance has the symbol uppercase letter D and is defined as the length of the path traveled, and it is measured in meters, and it is a scalar quantity, meaning that it has magnitude only. So if we consider an object that travels a path where it moves 3 meters upwards and then 5 meters to the right and then 7 meters downwards and then 4 meters to the right, we can say that the distance traveled by this object is the total length of that path traveled, which is the sum of all of those movements, that is 3 meters plus 5 meters plus 7 meters plus 4 meters, which gives us a resultant distance of 19 meters, meaning this object has traveled a distance of 19 meters, and since it is a scalar quantity, there is no direction required. Displacement, on the other hand, has the symbol x, often denoted with a line on it to remind us that it is a vector quantity, and it is defined as the straight line from the starting point to the end point of a journey. So we would find the displacement of this object by drawing a straight line from the starting point to the end point of this journey, and that would be defined as our displacement. We would often be required to use Pythagoras to find the exact value of that displacement, and we can do that by seeing that the displacement to the right is a total of 5 plus 4, which is 9 meters, and the displacement in the vertical plane is 3 minus 7, which would then be 4 meters downward. So we can then calculate the displacement of this object using Pythagoras, saying that this being a right-angled triangle, our displacement squared, the hypotenuse of that triangle, is equal to the square root of both of these sides, which means that we can then solve to find that the displacement of this object would be 9.85 meters. Now we can very clearly see there's a big difference between the distance and displacement of this object, and that comes from the definition, where distance is the length of the path traveled and displacement is simply the straight line path from the start point to the end point of a journey. Obviously, since displacement is a vector, it is important for us to define the direction, where we would most commonly use trigonometry to define the direction in terms of some angle theta that would be measured either from the vertical or from the horizontal. Speed is defined as the rate at which an object covers distance. It is measured in meters per second, and it has the symbol uppercase letter S. So in our previous example, we calculated the distance covered by this object, where we know that distance is the length of the path taken. We said the distance covered was 19 meters. Now, if we know that this object covered that distance in 4 seconds, then we can calculate the speed using the simple formula: speed is equal to distance over time, where the distance we know was covered as 19 meters. The time given was 4 seconds, which means that the speed of this object was 4.75 meters per second. Now, just as there's a difference between distance and displacement, there's also a difference between speed and velocity, where velocity is defined as the rate of change of displacement. It has the symbol v, often also written with a line on top of it to remind us that it is a vector quantity, therefore it must have magnitude and direction, and it is also measured in meters per second. The difference here now is that in order to calculate the velocity of this object, the definition says it is the rate of change of displacement. So where speed is distance over time, velocity is displacement over time. You will note that we sometimes write displacement as delta x, meaning the change in position. And our displacement here, we calculated as 9.85 meters, the distance from the starting point to the end point of that journey. And it still took this object 4 seconds to move from that starting point to the end point, which means that the velocity of this object is very different to its speed. The velocity is 2.46 meters per second. And once again, it is important to remember that velocity is a vector quantity and therefore must have direction. And the direction of the velocity will be the same as the direction of the displacement, which was calculated using trigonometry. And so we say that the final answer here is that the velocity of this object is 2.46 meters per second at an angle of 23.96 degrees. It's important to understand the difference between speed and velocity. The one is a vector quantity and the other is a scalar quantity. Velocity is far more commonly used, and it's important to remember that velocities must always be given with a direction. The normal force is the force that acts perpendicularly upwards from the surface with which an object is in contact. So there are 3 common places where this comes up. The first one is with an object that is at rest on a surface. Now we know that that object, since it has mass, must have a force of gravity acting on it. We can calculate that force of gravity by taking the mass of that object, which is given as 100 kilograms, multiplying it by gravitational acceleration constant of 9.8 to find that there is a 980 Newton force acting downward on this object. Now, we know that this object is not sinking into the surface because it is at rest, which must mean that there is an opposing force that is acting upward. And that is the force that the ground applies upward on that object, and that is known as the normal force, depicted with an N or sometimes F of N. The way in which we calculate the magnitude of that force is by using Newton's first law, which tells us that since this object is at rest, that must mean that the net force acting on this object is 0. The net force in this case is made up of the force of gravity that is opposed by the normal force. I have written this as Fg minus N. It is also acceptable to write it as Fg plus N and then take the sign into account at the end of your calculation. Either way, what you find is that your normal force in this case is equal but opposite to the gravitational force. So in this case, the normal force must be 980 newtons upwards, which makes sense because it is opposing the gravitational force and stopping the object from sinking into the surface. The second example is one where we have the same object that is now also has an applied force of 500 newtons attempting to lift the object upward. So now we know once again the gravitational force on this object does not change. It is also a 100 kilogram object, which means the gravitational force is also 980 newtons downward. The difference now is that there are 2 forces that are acting upward, those being the normal force and the applied force. So again, by Newton's first law, since this object is not moving, we can say that the net force acting on that object is 0. The net force is made up of all the forces acting downward minus the forces that are acting upward, the normal force and the applied force, which is then also equal to 0. And we can use that once again to calculate our magnitude for the normal force, as in this case, the force of gravity minus the applied force, which is 980 minus 500, which tells us then that the ground is exerting a force of 480 newtons upwards, which is combined or together with this applied force is equal but opposite to the gravitational force pulling the object downward. The final example is of an object that is on an inclined plane. That becomes slightly more complicated because in this case the gravitational force is not equal but opposite to the normal force, because as we can see, the gravitational force acts vertically downwards, whereas the normal force is acting perpendicular to the surface. by definition. In order then to calculate the value for that normal force, we need to find the component of gravity that acts opposite or perpendicular to that surface. We do that by resolving the gravitational force into its two components, Fg perpendicular because it is perpendicular to the surface, and Fg parallel, which is not necessary at the moment. We can find that by knowing that this angle theta here is also 35, which then tells us that our perpendicular angle Fg perpendicular is equal to Fg cos of theta, where the force of gravity remains the same, 100 times 9.8, 980, cos of that angle 35, which tells us that the perpendicular component of gravity is 802.77 newtons, and that is into the slope. It is not vertically downward, it is the force that is pulling the object into the slope. From there, to calculate our normal force, we use Newton's first law again, but now looking in this plane that is perpendicular to the surface, where we say F net is equal to 0. In this case, F net is made up of Fg perpendicular acting opposite to the normal force, and therefore our normal force is equal but opposite to the perpendicular component of gravity, and therefore we can say that our normal force is 802.77 newtons out of the slope. Friction is the force that opposes the motion of an object and acts parallel to the surface with which an object is in contact. The friction is calculated by taking the product of the coefficient of friction and the normal force. The coefficient of friction is something that is specific to the interaction between one object and its surface, and it can be calculated by taking the ratio of the frictional force between those two objects and the normal force that the surface exerts on that object. Since it is a ratio, it will not have any units, and the values for this coefficient of friction are typically between 0 and 1. So in a typical example, as we have here, a 100 kilogram object with an applied force attempting to move the object to the left. In order to start this object moving, it is first necessary to overcome the static friction, also known as the static friction maximum, Fs max, which can be calculated by taking the product of the static friction coefficient and the normal force. The coefficient of static friction has been given as 0.4, the normal force calculated as 980, which means that our static friction maximum is 392 newtons. Now, static friction and all friction is a reactive force, meaning that it only acts to counter the force that is attempting to move the object. So that means that this static friction maximum is the maximum frictional force that this object will exert before it starts moving. So in a typical example, if the applied force was 0, there is no attempted motion. So since the applied force is 0, the frictional force is also 0, since friction only attempts to oppose motion. In a second example, if we now said that that applied force was 200 newtons, we can now very clearly see that there is a force of 200 newtons that is attempting to pull the object towards the left. But as we can see, that 200 Newton force is not great enough to overcome the static friction maximum, which means that static friction maximum reacts by only exerting a 200 Newton frictional force, the result of which being that the net force on this object is 0 and the object does not move, and it is therefore opposed motion once again. As we can see, this applied force could be any value between 0 and 392 before this object would move. The applied force would have to be greater than the friction maximum, static friction maximum, in order for this object to be moving. The reason why the static friction is generally higher than the kinetic friction is because the two surfaces tend to form a cold weld in which the molecules of their surfaces overlap with each other, and essentially stick together like two pieces of sandpaper that are overlapping. But once the applied force has exceeded the static friction maximum, in this example I'm using an applied force of 400 newtons, once that has happened, we can now say the object is in motion. As soon as the object is in motion, static friction no longer applies. So the only friction that now applies is known as kinetic friction, which can be calculated by taking the coefficient of kinetic friction, which is slightly less than that of static friction, which is 0.3 in this case, multiplied by the normal force of 980 to find that the kinetic friction is 294 newtons. We know that this frictional force always opposes motion, acts in the opposite direction, and parallel to the surface. And then the final thing that we can see here is that this frictional force does not stop the object from moving, because we have an applied force that is greater than the kinetic friction, which in this case means that this object has a net force that is acting on it of 106 newtons. In the simplest mechanics questions, the forces are either perpendicular to each other or parallel to each other, which makes it easy either to add or subtract forces if they act in the same or opposite directions, and to use Pythagoras to determine a resultant force when they act perpendicularly to each other. Now, what's far more realistic is forces that act at various angles to each other, as we've got in this example over here. We've got a 100 kilogram object that is being pulled or attempting to be pulled with a 300 Newton force to the left, and then an applied force that is being applied at an angle of 40 degrees to the horizontal with a value or magnitude of 700 newtons. Now, since these forces are not exactly opposite to each other or exactly perpendicular to each other, we cannot simply add them or use Pythagoras. What becomes important for us to do here is to resolve the force into its components. And the way that we do that is we can redraw this applied force over here, and we can show that this applied force has two components, meaning two forces that make it up. Those two forces are the part of that applied force that is pulling it parallel to the surface, and we can call that FA parallel, also sometimes referred to as FAX because it is acting in the X direction. And then the other force which we can draw is the component of the applied force that is acting vertically upwards or perpendicular to the surface, FA perpendicular. We can also see, since we are allowed to redraw these forces wherever we want, this FA perpendicular could also be drawn there, and FA parallel could also be drawn there. Either way, the result is the same. We can now use trigonometry to find the values for those respective forces, and we can say that since we know that sine of theta is equal to the opposite side of the triangle over the hypotenuse, in this case that is FA perpendicular over FA, which can be rewritten as FA perpendicular is equal to FA sine of theta. We can then substitute those values that we have here. FA was given as 700 newtons and theta was given as 40 degrees, which means that the component of A that is lifting this object upward is 449.95 newtons, and that is an upward force. In the same way, we can calculate FA parallel by saying that since that is the adjacent side over the hypotenuse, FA parallel, the component of A that acts parallel to the surface, is equal to FA cos of theta. In this case, that is 700 cos of 40, which is 536.23 newtons, and that is acting to the right. Now that we have resolved this vector into components, we can now easily compare because we can now look and see that there are only two forces acting horizontally. There is, we can say that it is the net force horizontal, or parallel is also an option, and we can say that that is equal to the force pulling it to the right. In this case, that is FA parallel minus the force pulling it to the left, which is tension, and we can calculate the net horizontal force and see that that is 536.23 newtons that is acting to the right minus the 300 newtons acting to the left. So there is a net force of 236.23 newtons acting towards the right. We can then use that in determining whether or not it can overcome friction, but before we do that, we need to first determine what the normal force acting on this object is. Once again, this object is clearly not being lifted off the surface or sinking into the surface, which means that our net vertical force, also known as the net perpendicular force or the net Y force, must be equal to the force of gravity that is pulling this object downward, minus the two forces that are essentially lifting or pushing the object upwards, those being the normal force and the perpendicular component of the applied force. So our net vertical force, Fg, minus the normal force, minus our Fa perpendicular, and we can rewrite that to find that our normal force is equal to our force of gravity minus Fa perpendicular, in this case the force of gravity, mass times gravity, 980, minus the perpendicular applied force, 449.95, which then gives us a net vertical force of 530.05 newtons upwards. So once we have that, we can now use it to calculate our frictional force. So as you can see, it is important to resolve forces into components so that they can be compared by either being exactly equal or exactly in opposite directions to each other. The inclined plane is a problem that is commonly set up in some version of this format that we have here, where you have an object with a mass m that is placed on a slope or an incline that is inclined to the horizontal at some angle theta. Now, what this changes is that the force of gravity now acts in essentially two planes. The one plane being the force of gravity, or the part or the component of gravity that is pulling that object down the slope, and then the other component of gravity that is pulling the object into the slope. And we can find these by first realizing that the force of gravity is always a force that acts vertically downwards to the center of the earth, and that is calculated by taking the product of the object's mass multiplied by gravitational acceleration. Once we have done that, we can then resolve this into those two components. Those components being the component of gravity that pulls this object into the slope, and we call that Fg perpendicular. The reason for that being that this force is always perpendicular to the slope. The second component is the component of gravity that is pulling this object down the slope, and we call that Fg parallel. The reason for that this component acts parallel to the slope, in this case downwards. What we have now done is we have created a right-angled triangle, with the right angle being here. We can use geometry to find that this angle theta that the slope is inclined at is also equal to this angle theta over here. And now that we have a right-angled triangle, we can see that the angle opposite to this is Fg parallel, the angle adjacent to it is Fg perpendicular, and the hypotenuse is the original force of gravity. So we can use trigonometry now to find out what the values of each of those components is by seeing that the opposite side is Fg parallel, and we know that sine of theta is equal to the opposite side of a triangle over the hypotenuse of that triangle, which in this case, the opposite being Fg parallel and the hypotenuse being Fg, which can then be simplified to give us the formula Fg parallel is equal to the force of gravity multiplied by sine of that incline. Similarly, we can do a calculation to find that the perpendicular component of the gravitational force is always equal to Fg cos of theta. In mechanics, there are often multiple forces acting on a single object, which makes it very important for us to be able to draw a diagram that helps us to understand those forces and how they relate to each other. So there are largely two main types of diagrams that we do. The most common one, though, is the free body diagram. What the free body diagram does is it simplifies the drawing by starting out with the assumption that the object can be condensed to a single point or a dot. This normally represents the center of mass of that object. And then all forces must be drawn pointing away from that center of mass. So for example, we know that the gravitational force acting on this object over here, we are, for interest sake, we are dealing with this object over here. It is a dog that is being pulled by its owner, and what we can see is that there's a force of gravity that acts downward on the center of mass of this object. We also know that since this dog is standing on the ground, we know that there is going to be a normal force that the ground exerts upward on this object. Then we can see that there is a tension force, the force that the leash is exerting on that object, the tension force there that is acting at some angle. We are allowed to indicate that angle if it is known in this diagram. And finally, we can see that this object is not moving, which means that there must be some kind of frictional force acting on this object. And we know that frictional forces always act opposite to the direction of motion and parallel to the slope. What we can see here is we have now drawn a free body diagram. It is important to label this free body diagram with a key so that anyone reading it would know that Fg represents the force of gravity, T represents the tension, N represents the normal force, and F represents the frictional force, and that must be included in the key. A couple of important notes here. You may not draw components of forces onto a free body diagram. So there's a tension force acting at an angle. You may not show the horizontal and vertical components of that tension force, because you are then implying that those forces are also acting on this object. Another thing you may not do is you may not draw arrows that end on this center of mass. The arrows must always be directed away from that object. And then finally, when drawing free body diagrams, you can, if there are two forces acting in the same direction, you can draw them or represent them in the following way. You show that it is an arrow that acts in the same direction. The other common type of diagram is known as a force vector diagram. This one gives a bit more information in that it shows where and how the forces act on that object. So we would now simplify the object to a block, and you show the direction that the force acts. So you would show that this tension force acts on the corner of the object and it acts upward at an angle. The difference now is that we know the frictional force acts along the bottom surface of this object. We know that the force of gravity acts from the center of mass of that object, and we know that the normal force also acts on the bottom surface. So you would label this object, and so this is a force vector diagram. Again, a key is important, but what we are showing here is we are showing where the forces act as well as the direction in which those forces act. But once again, the free body diagram is the far more common one, where you show vectors only pointing away from the diagram. You show the object as a center of mass or as a single dot, and you represent it with a key, and you make sure that you do not ever show any components of forces on that diagram. Newton's first law states that an object continues in its state of rest or uniform velocity until a non-zero net force acts on it. Now, there are two important aspects of this definition that help to explain the concept. The first one is the state of motion, which they've defined here as either a state of rest or of uniform velocity. So what this tells us is it tells us that when the net force acting on an object is zero, as it says here, until a non-zero net force acts on an object, that implies that the current net force is zero. So what they're saying is that when the net force acting on an object is zero, there are two options for the motion of an object. The first is the one that we all understand very well. This is the option of an object that is on the ground. We know that while that object is on the ground, there's a force of gravity pulling it downward, but we know that the ground exerts a normal force upward on that object, and therefore the net force on that object is zero, and we can then safely say that object is not moving. The second one is slightly less intuitive, but essentially this is for an object traveling at a constant velocity. So we know that when you're in a car and the car is traveling at a constant velocity of 120 kilometers per hour, we know that there's a force of gravity pulling it downward, there's a normal force pulling it upward. We know that the engine is applying a force that pushes the car forward, and we know that there's also friction of the tires and friction or a drag force that holds it back, but we know that the force that the engine is applying forward is equal to the frictional force and the drag force that's holding it back, which is why the velocity remains the same. So all that Newton's first law tells us is it just says that for as long as the net force acting on an object is zero, it will either travel at a constant velocity or it will remain at rest, which we can also simplify to just say the velocity of an object at rest is zero. It is very important when writing this definition to specify that it is a net force acting on the object, because we can very clearly see that there are a number of forces acting on both of these objects, and that has no impact on the state of motion. The impact is had or made by the net force specifically. Newton's second law states that when a non-zero net force acts on an object, the object will accelerate in the direction of the net force, and the acceleration is directly proportional to the force and inversely proportional to the mass of the object. So where Newton's first law explained that when the net force is equal to zero, therefore the velocity is equal to zero, Newton's second law now tells us what happens when that net force is not equal to zero. And it says that the object will accelerate. And we can see that when somebody is trying to push start a car, we know that initially when you try to push a car, there's too much friction and you can't start the car moving. But as soon as the applied force that you are applying on that car is big enough to overcome the static frictional force of that car, we know that this car now has a net force acting on it that is greater than zero, which means that this car is going to accelerate in the direction of that force. Now, by that same standard, we understand that if instead of trying to push start a car, you were trying to push start a truck that is much heavier with a greater mass, we know that you can still apply the same force. It is still possible that there would be a net force that is greater than zero, but because the mass is so much bigger, the acceleration is going to be far smaller, which is why we say that the acceleration is inversely proportional to the mass of the object, or acceleration is directly proportional to the inverse of mass of the object, which is how it's written here. The second point that it makes is that we know that if instead of one person trying to push start this car, you had 2 or 3 people trying to push start this car, meaning that the force that is applied is far greater, the applied force is greater, which means that our net force is bigger, which would then imply that the acceleration is bigger, which is why we are then able to say that this acceleration is directly proportional to the size of the force. The bigger the force is, the bigger the acceleration. This can all be summarized into the Newton's second law equation, which tells us the net force acting on an object is equal to the mass of that object multiplied by the acceleration of that object. Some common mistakes when asked for the definition for Newton's second law are to leave out the second part that explains the relationships between acceleration and mass and acceleration and force. The second common problem is to say that force is directly proportional instead of acceleration. So these underlined words are incredibly important when writing down a comprehensive definition for Newton's second law. Newton's third law states that when object A exerts a force on object B simultaneously exerts a force of equal magnitude in the opposite direction on A. Now, the first thing that we need to understand here is some notation. We have over here object A, a person that is applying a force on a box that is trying to push the box across the floor. And the way we would write this, or the way we can write this, is when we write FAB, what that means is the force that A exerts on B. And by Newton's third law, what that says to us is that the force that A exerts on B is exactly equal to the force that B exerts on A, but in the opposite direction, hence the negative sign. What this tells us is that when we are trying to push an object, the reason why we feel that pressure on our hands is because that object is applying a force equal in magnitude but opposite in direction back on us. Now, a common question that comes up from this is, if the forces are always equal but opposite, how is it possible that the one object moves while the other doesn't? And we resolve that by drawing a free body diagram for each one of these objects. So object A, we can show has the force that B is exerting on it, FBA. It obviously also has a gravitational force acting on it and a normal force. And object A will have some kind of frictional force that is opposing that force that B is exerting on it. Then again, if we look at object B, so this was object A here, if we look at object B, we can see that B has the force that A is exerting on it, FAB, to the right. It also has a frictional force acting to the left. It has a force of gravity and a normal force. So the first thing to notice here is that FAB and FBA are acting on different objects, and therefore the net force for these two objects would not include both of these forces, which is why they do not cancel. The reason why hopefully this person would be able to push the object is because they have shoes that have grip on the floor, and that frictional force is able to oppose the force that the box exerts back on that person, while the person is strong enough to be able to overcome the frictional force between the box and the floor. Newton's third law is often misquoted as every action has an equal and opposite reaction, where what we can see here very clearly is that the third law only applies to forces being exerted on objects. It just says that when one object exerts a force on another object, that object will exert a force equal in magnitude but opposite in direction back on the original object. Newton's law of universal gravitation states that each body in the universe attracts every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Important to note here that this body that is referred to here, or each body that is referred to, is a body that has mass. So they're basically saying there's a force of attraction that exists between every two objects of mass within the universe. Now, we can use this definition to derive the formula, and obviously you can then use the formula to derive the definition. But the first thing that this says to us is that the force is directly proportional to the product of their masses. So we know we are dealing with two objects. Each of them has a separate mass, so the product of their masses just means the one mass multiplied by the other. So this tells us that as the masses masses of two objects increase, we can then see that the force between those two objects would also increase, and we know that a direct proportion there just means that as the product increases, so does the force. The second part of this definition refers to what's called the inverse square law and says that the force is inversely proportional to the square of the distance between their centers. So what that tells us is it says that F is inversely proportional to the square of the distance between their centers. Very important here to specify that it is the distance between their centers, because very often this law is used for very big objects where there's a big difference between the center of an object and the surface of the object. So what this actually tells us is it tells us that the force is directly proportional to 1 over r squared, which can be written or drawn on a graph like this, showing a direct proportion. We know that a straight line means direct proportion. But that is not really telling the whole story of what the relationship is between force and distance, because what we need to understand here is that as the force increases, the distance between the two objects would decrease, or more likely, as the distance between two objects increases, the force would decrease. And so we show that with a graph of force versus distance between them squared, and this shows us that when the two objects are very far apart, the force is very small, and as the objects get closer together, the force increases. And so these two graphs are very important. This over here is referred to as the inverse square law. So what we can do by combining these two relationships, we can find that the force is directly proportional to the product of the masses of the objects over the distance between their centers squared. And in order to make this into an equation, we introduce the universal gravitational constant, which then tells us that the force is equal to the gravitational constant multiplied by the product of the two masses divided by the distance between these two object centers squared, where we know that the universal gravitational constant is 6.67 times 10 to the power of minus 11 Newton meters squared per kilogram squared. This is always a constant for every part of the universe, and so the three factors that we have power over would be the masses and the distance between those two objects. We can now also see why it's possible to derive the definition from the formula, because this formula tells us that there is a force between every two objects with mass, and that force is directly proportional to the product of their masses and inversely proportional to the distance between their centers squared.